Good morning, everyone. Thanks a lot. I remember I have 40 minutes, and I always try to stay on track in order to give more than enough time to questions. So let me put just a timer. Okay. So my name is Maurizio Pajola. I'm staff scientist at the INAF Astronomical Observatory of Padova, and today I'm showing you what we have done so far with the OSIRIS-REx sample return. So just a super brief summary of myself. Again, I'm working at the Astronomical Observatory of Padova, and I love analyzing images of solar system bodies. I'm working with European Space Agency's instruments on board, for example, Rosetta, the OSIRIS cameras, then the Cassis stereo camera on board the ExoMars, focusing on the surface of Mars, of course, and then also the Symbiosis suite on board the Bepi Colombo mission that is flying towards Mercury. Since November 2017, I had the possibility to enter and to join the OSIRIS-REx mission because there was this open call for not only NASA scientists, but also for scientists all over the world. And at the end, they selected 13 scientists, and out of which 12 are from US-based universities or like NASA Center. And I was the only one, let's say, from an European country or somewhere else. So what is OSIRIS-REx? OSIRIS-REx is the third missions of NASA New Frontier program. As you know, NASA has different programs, has the Discovery programs that has a limit cap of maximum amount of $800 million. Then there is, of course, the large missions, like, for example, Cassini or Curiosity or Perseverance, that is well above $1 gigadollar. So it can also reach 2 or 2.7. And then there is this New Frontier mission set that has a cap around 1 million, and around $200,000. So the first one of this New Frontier mission was New Horizons, the spacecraft that flew past Pluto in July 2015, and then also made us the possibility to observe Arrokoth, the TNO, the Trans-Neptunian object that was observed in January 2019. And then the second New Frontier mission was and is Juno. INAF is involved a lot with the Juno mission, and actually this spacecraft is still orbiting around Jupiter and from pole to pole observing the magnetosphere, and now also becoming kind of an orbiter observing the icy satellite Io of Jupiter. But OSIRIS-REx is the third one, and is the first US mission that has the main goal of catching and grabbing samples from the surface of an asteroid, that is asteroid Bennu. And I will explain you why later. And it was launched from Florida, Cape Canaveral, on September 8th, 2016. So the main 5 objectives are now here detailed. You know, the Americans are really strict from this perspective, and the main goals have to be fulfilled. But really the most important one, returning a sample of a carbonaceous asteroid, in this case Bennu, with an amount that is larger than 60 grams. At the beginning, people from the mission were thinking that less than 60 grams was a failure of the mission. You know that Americans are kind of really strict about that. But in reality, you will see later that it was taken much more than 60 grams. So this is the main goal. Everything else is below this important goal. The second one, of course, is to map the properties, the chemistry, and also the mineralogy of this asteroid, that is Bennu, and it is a primitive carbonaceous asteroid. And the most important thing is to characterize all the different properties with different instruments. You will see later what kind of instruments we have on board the spacecraft. Then the third main goal is very, very similar to the one that Rosetta had. So to document the texture, morphology, but also geochemistry and the texture, the properties of the regolith, but with an unprecedented spatial scale. So with Rosetta, we were having images with centimeter scale, meter scale. Now we are going to sub-millimeter scale. Another objective is to study the Yorp effect, which is this effect that is kind of changing the orbit of small bodies below 5 kilometers inside. So to measure this Yorp effect for Bennu, because Bennu is one of the considered potentially hazardous asteroids, and it has a probability that is not zero to impact the Earth in 2150 something. So the idea is we have to understand if Bennu's orbit will remain the same in the next couple of 100 years, or it will be changed due to this effect. And then, of course, here there is a great image, but our main objective, the number 5 objective, was to have, okay, the amount of the surface, knowing all the different properties in situ, but then make a comparison with all the other asteroids that are observed with a spacecraft or with orbiting satellites of the Earth, that can get spectra of asteroids. But of course, we cannot have 100 OSIRIS-REx missions. So we kind of need a connection between what we observe in situ and what we observe from Earth or orbiting satellites. So to have a kind of connection between the two. So to wrap up, what is OSIRIS-REx is a complex name and is a sort of acronym, is an acronym that stands for origins, because of course we are looking to get samples from a pristine asteroid, that is Bennu. Spectral interpretation, so we are also observing the surface with spectrometers, not only in the near infrared, but also in the far infrared. Then resource identification, we have to identify the first resources that we can grab from the surface of the asteroid and then bring back home. And of course, security, because we are talking about an asteroid, the Near-Earth Asteroid, that has a chance that is non-zero to impact the Earth in the next couple of 100 years. And of course, regolith explorer, because we are exploring with a spatial scale that is unprecedented the surface of this asteroid. So, but why is it important to get a sampled return from an asteroid? Because basically asteroids are considered the leftovers of the building blocks of the solar system. So asteroids and comets, they have different properties, but they are kind of these leftovers. Billions of asteroids, of course, and comets crash together to form Earth and other planetary bodies in the solar system. But what we can see right now and orbiting the sun are really the remains of this formation. And of course, one can say, okay, but why do we need an asteroid sample? Actually, in reality, we have a lot of meteorites impacting the Earth, and we can already analyze them in laboratories. This is true, but the problem is that most of the time we don't really have any clues about. We have a general idea where they are coming from, but we don't have a perfect, let's say, and a detailed context of these bodies. So we know that they are coming from an asteroid in the main belt, in the inner part or the outer part, or as a near-Earth object, but we don't really know we don't have a contextualization of it. So if we have a look at all the possible targets that were observed with dedicated missions, mostly NASA missions, but also European missions, like for example, the Rosetta one that was making a flyby of asteroid Steins and Lutetia, we see that there are really 3 different targets where we have the chance to get samples. One, of course, is the Hayabusa target from the Itokawa asteroid, that in reality had a lot of problems, but it looks like it was bringing less than micrograms to the surface of the Earth. Then, of course, we have now on Earth, safe and sound, the samples from Hayabusa 2 mission of the Ryugu asteroid, and then of course there will be the OSIRIS-REx mission, that is the one bringing the largest mass of samples back home. So, but how was asteroid Bennu chosen? In reality, you know that there are more than 500,000 asteroids, even more in the solar system. Out of these 500,000, there are just 7,000 near-Earth asteroids with specific dimensions that can be of interest for the mission. Only 192 have an inclination on the ecliptic that is as low as possible in order not to use too much propellant to reach them. Then 26 have a diameter that is larger than 200 meters. Why do we care about asteroids that are larger than 200 meters? Because we know that asteroids smaller than 200 meters can be fast rotator. And as you will see, Bennu rotates in a little bit less than 5 hours. And in reality, when you have a fast rotator, there is a high chance that all the boulders, all the pebbles that are on the surface itself, they. So of course, if you want to do something as scary as going down to the surface and grab a sample, something that is not too much fast, and of course, it's not throwing you pieces of the surface in order, to not to destroy and not to jeopardize the mission. Then 5 of these 26 are carbon rich. So we are talking about asteroids that are pristine. They're not metallic. They're not made of silicates. So they were not heated up by the sun, but they are really considered the pristine bodies, carbonaceous chondrite, and so on, are really representing the first conditions for formation of the solar system. And finally, we get Bennu. Out of these 5 carbon-rich asteroids, we have also Ryugu. So the other Hayabusa 2 mission was really in this list. So, but what about the spacecraft? As you can see, the OSIRIS-REx instrument deck is characterized by different instruments. The one that I'm using the most is the OCAMS camera. It's 3 different cameras observing in the visible, specific filters, the surface of the asteroid. Then we have a Canadian instrument that is the OLA, that is the OSIRIS-REx Laser Altimeter. That is an impressive instrument that allowed us to get shape models, so reconstructed 3D surface of the asteroid down to resolutions of a centimeter, which is impressive. Then we have the OTES, that is the OSIRIS-REx Thermal Emission Spectrometer. This is important to study the far infrared side of the spectrum of the asteroid, and then to infer the different properties of the grain sizes, for example, characterizing the surface itself. Then we have OVIRS, that is the visible and infrared spectrometer. This is a spectrometer similar like to the Virtus one on board the Rosetta spacecraft, but of course this one is an American one, and it looks the surface and it analyzes the surface in the visible and near infrared part of the spectrum. And then we have Rexis, which is an instrument that was observing the surface in the observing the surface, the reflected X-rays coming from the surface of the asteroid itself. It was working, but in reality, it was just an experiment instrument made by a student of the Massachusetts Institute of Technology. And basically, what they observed is that the asteroid was not really reflecting too much in the X-ray, and it was not considered a failure, but it was not giving the desired results. And then there is one of the most important instrument, let's say, of the spacecraft itself. It's the TACSAM. The TACSAM is the robotic arm that is the only part of the spacecraft that is really touching the surface. And here you have the head of the sampling system, that is this one right here. You will see later with all the samples in a GIF that the mission have prepared. And here you can see that there are 3 different tanks with high pressure nitrogen. That is the one that was used, now I can use the past tense, that was used in order to grab the sample from the surface. So how TACSAM is working? Basically, gas is coming with a tube, high pressure nitrogen gas is coming from the tube inside this area right here. Now you see that there is this circular feature where you have all these different holes. When this gas is ejected towards the surface where there is the regolith, then of course there is turbulence, and then all this material is sucked inside the system. But the only way for gas to go out is with all these little holes taken aside. All the different grains are sucked inside. There is this mylar flap. They are lifted up, and then all these different grains are located inside this circular corona surrounding the entire head. And then the gas is being lifted up. Of course, here we have to keep in mind two different measurements. The first one is the 25 centimeters space right here. That is the hole where the grains are sucked inside. And then there is the 2 centimeter diameter, that is the maximum diameter that is allowed for grains to come inside and to stay here. In reality, you will see later that we had grains that are much bigger than 2 centimeters, and in reality, they were blocking this mylar flap. Okay, so this is the full schedule of the mission, and in reality, we have arrived in December 2019. In December 2018, I will show you now pictures. Then we have the detailed surveys. We start the recon phases in order to site select an area on the surface of the asteroid, and then beginning of December 2019, we start a sample acquisition campaign. At the beginning, it was foreseen on July, but in reality, TAC occurred in October 2020. So this is a GIF of the first images we got of asteroid Bennu. Here, what you have is an image of August 17, 2018. And I really like this picture because it reminds me of Rosetta when we have the first glimpse of Comet 67P. And you just see a small dot in the sky, moving in the sky. Then in October 13, 2018, we were close to 32,000 kilometers, in reality 33,000 kilometers. And it was the first day where we passed with a Polycam camera, the biggest camera we have on board the spacecraft. We were having more than 1 pixel of the asteroid. Then in reality, we are going fast, as you can see. In October 14, 2018, we have a range to Bennu 1 kilometers, 1,000 kilometers, 1.7 pixels. Then 9,000 kilometers, around 4 pixels. Then in October 28, just 14 days later, we are around 650 kilometers far from the surface, and the scale now of the image is around 9 meters per pixels. Then in October 29, we are 250 kilometers farther from the surface, and the scale is 3.4. And as you can see, in November 13, we are around 146 kilometers, and we start seeing that there are boulders, that there are possibly craters on the surface, and then there is kind of a surface variegation on it. And then in November 25, we have a distance of around 80 kilometers from the surface, and this image is gorgeous, but it was not only gorgeous, but it was really, really scary from an engineering perspective, because we have to find a safe landing spot here where to grab samples, and it's not easy. And the scale here is 1 meter per pixel. And then this is another gorgeous image of the asteroid Bennu, taken in December 1st, 2018. Here we are just 29 kilometers from the surface, and the pixel scale is 40 centimeters, which means that basically you can recognize and distinguish features that are larger than 1.2 meters. And then that's another image that, of course, was filling the full field of view of the Polycam instrument. And this is 70 meters of the field of view. And as you can see, boulders are everywhere. So we are supposed to find a safe sampling site here. One thing that I mentioned is that the first idea of a sampling site was a flat surface of 50 meters. As you will see later during the site selection campaign, there will be no area on the surface of the asteroid that is as wide as 50 meters and as clear and as perfect as the engineers were hoping for. So just a little bit of science in order not only to give beautiful pictures and all these properties. So Bennu's rotation rate, what we put is that the Bennu's rotation rate is accelerating since 1999. But we were not able to distinguish between YORP or other different properties. But in reality, thanks to the first missions, we had the chance to observe that the rotation is accelerating, and it is mainly due to the effect. Then on the surface of Bennu, there are lots of minerals, and there are hydrated phyllosilicates, and also we have thermal emission spectra. Coming from OTES, we can see that there are specific absorption band, and we can see that there is also magnetite. Then what we can see that Bennu exhibits the expected spinning top shape. We have a surface that is called a diamond shape, and thanks to the mass determination and the density, we have a value, thanks to the mass determination and the volume, we have a density of 1.1. On top of that, we have the chance to detect that the full surface and the subsurface of Bennu has a 50% macroporosity. On top of that, Bennu has also a large albedo variation, because we see that the full surface is around 4%, but there are also areas with a maximum of larger than 15%. So there are bright patches that we will see later. They are constituted by silicates that cover specific of the surface, but in reality, most of it is extremely dark. And then another really important property, that is Bennu has a low thermal inertia. If we have a look at the specific thermal inertia that it has, we are expecting, making comparison together with the example or Mars, we are expecting kind of a surface that is by small grains and a surface that is constituted by dust. In reality, Bennu, as you have seen, it's kind of strange, because it's really the first time, together with the other aspects by Hayabusa 2 mission, that is characterized by big chunks of material, big boulders, but there is a huge macroporosity. That's why we have such a low density. But on top of that, we have still a low thermal inertia, but lots of boulders and not dust. That's why it was selected at the beginning as a sample target return mission. But the biggest surprise is that Bennu is also an active asteroid. So this was not expected, of course. I was telling you that we were looking at an asteroid that was smaller than 500 meters, but larger than 200 meters. But in reality, why were we selecting above 200 meters? Because we didn't want to have chunks of material being ejected. In reality, we see for the first time that this asteroid has not a cometary-like activity, but sediments are ejected and are put into orbit. And these are kind of dangerous for surface analysis. Then, now I'm kind of shifting towards the sampling site selection properties. We are looking for 50-meter sites, but in reality, as you can see in the map on the left, everything is red. Nothing on the surface of Bennu satisfies all the criteria. So we have to end up with a solution where basically the engineers were trying to find smaller areas, definitely smaller than 50 meter. And at the end, we end up with solutions not larger than 20 meters. And this crater, as you can see, is not a safe area. There are big chunks of material that can jeopardize the mission. So what do we usually do with the sampling site selection process? We have a 3D shape model. We compute slopes on the surface of the asteroid. This is done thanks to images and also LiDAR, so the laser altimeter instrument. Then we have high resolution imaging and colors. In this case, of course, you see a gray surface, but basically you see that there are different properties in albedo. There are chunks of that are bright, others that are dark. Then we create 3D anaglyphs in order to have an idea about the possible depth of sites. And then one of the main tasks that I also had was to boulder and pebbles count in order to say, okay, we have a criterion, basically want to land on an area that has just chunks of that are smaller than 2 centimeters. In reality, for example, when there is a red line, it's larger than 21 centimeter. So this site basically is not right. Of course, we had more than 100 different sites because scientists were suggesting all different exciting places, but in reality, we ended up with final 4 that were located a couple close to the equator, 1 Nightingale to the north and 1 Sandpiper to the south. And as you can see here, it was given names of birds. So I had a chance. I'm not an English speaker, but I had a chance to learn different names of birds all around, like for example, nightingale, kingfisher, osprey, and sandpiper. And Nightingale in reality was selected as the final one. It is located, as you can see, in a small crater that is 10 meters. It is, in reality, this small crater is located inside a much larger crater that is 140 meters. It's close to Bennu's North Pole. It has a lot of fine-grained material, as you can see right here. And given that it's very, very dark with kind of variegation, but it's located to the north, it has one of the lowest temperature shift on the full surface. So it's a thin site where to grab samples from the surface. And it's regolith, as you can see here, there are bright patches, bright boulders. We have variegation, so we have diverse materials. And also, which is the main reason we selected Bennu as the final asteroid. It's carbon-rich minerals. There is a lot of carbon-rich minerals on the surface. And here I really love this infographic because it provides you a glimpse of the real dimensions of the site with respect, for example, of a parking spot you can find in the US or in Italy. So the primary sampling site was selected to be Nightingale, and the backup sampling site was selected to be Osprey. But as you can see, both in Osprey, there is a huge boulder. It's called 12 o'clock rock right here. And on the Nightingale site, it's kind of a dangerous one because a huge 10-meter wide boulder right to the site. So as engineers, finally, of Lockheed Martin admitted, basically, Nightingale and Osprey, it's the less bad site we could get. It's not a good site, but it's at least the one more feasible, I have to say, with respect to all the other areas we had on the island. So let's do, I still have 13 minutes. Let's do a small flyover on Nightingale so that you can have a glimpse and an idea about this big boulder that is scary and is extreme to the sampling site. So we go down, as you can see, there is this crater right here. You kind of feel like there is a depression, and it is the area where there was the sampling site selection and then was the sampling site acquisition. And then we just back off a little bit. Okay, this is an idea site, as you can see, both on one area and both on the other side of the sampling. There are dangers. And just to provide you an example about the sampling tag acquisition mechanism, the corona that I was showing you of taxam. So the outer diameter is 30 centimeters, while the inner one is 21. So if we kind of project this one on the surface of the full landing site, you see, in reality, we can sense on the surface. So on the 20th October 2020, there was tag, and this is a GIF. I don't know if you can see it, but this is the GIF of the acquisition that we have on that day. It was really, really exciting. It was without any problem. There were specific acquisitions thanks to with the imaging recognition of the surface. But at the end, the surface, despite its roughness, was not. It was a positive one. There was a way to get lots and lots of samples. In reality, what happened is that we went down to the surface at a speed of less than 30 centimeters per second. And at some point, the surface was not really, in reality, the chance to be collecting gas from the tanks that I was telling you before in order to do mass and to grab as much sample as possible. We really penetrated the surface down to 50 centimeters. So we were not really, at the beginning, we were thinking to have something rocky that was stopping you. And that's why we were thinking of using all these gas in order to make a mess and in order to have these samples to be grabbed. But in reality, we had the possibility to penetrate for 50 centimeters. So basically, the system was already full well before ejecting all this gas. And then it was ejected this gas. And that's why you see all this mass of material that is going everywhere. In reality, the sample acquisition went extremely well. I can see here, there is on this area right here, there is a piece that is here is located, the mylar flap is at the circular location of the mylar flap. And here there is a grain that is much smaller, much bigger than 2 centimeters, that is leaving this mylar flap open. That's why at some point we could see after that there were grains leaving the spacecraft, leaving the sampling head. So what it was foreseen at the beginning was to make this mass measurement, putting the spacecraft to spin around its main axis with the arm that was fully extended before acquisition and then after acquisition, in order to understand what was the difference of the moment of inertia, and really to say have acquired 300 grams 0.2 or 1 kilo 620 grams. So, but in reality, the PI decided not to do that because we could see once we had the STO acquisition, the sample acquisition, we could see with our camera that there were this grain leaving the spacecraft. So it was really, really important, this decision, because we are convinced that it saved several grams that were leaving the spacecraft, leaving the system, several grams to be stored inside this part of the spacecraft, that is the return capsule. So on 27th of October 2020, this is another of the sampling acquisition head with all grains all together and well inside. The capsule was open, then it was, the tag head was inserted, and then it was, the arm was separated, and then the capsule was closed on the 28th of October 2020, without knowing the real mass, but expecting that it's more than 300 grams. Because we could see, for example, at the beginning, that the light was, when there were no grains inside, the light was passing through all these different holes, and we could see shadows on the other side of the taxon. But in reality, when we were getting this GIF and this image, we could see that there was no light on the other side, here and here. So basically, the full system is completely full. And on top of that, I have to say, are these kind of small holes that were scratching the surface. So even grains were on these small holes. Okay, now at the beginning we were not thinking to return back to Bennu because it could have been dangerous for the sample acquired, and for all these kind of maneuvers that you had to do to return to Bennu once you backed off from the surface the day of the acquisition. But in reality, the PI then decided that on April 7, 2021, we will return back there in order to see what kind of mess we have made on the surface of Bennu. So it will be great because it will be just a few months that the subsurface is exposed. So we are looking for to understand what are the possible colors below the surface itself. If below the surface we have pristine materials that we have, it's what we think of the asteroid itself, and then we will also make measurements not only from a camera perspective but also from thermal measurements, but also with a laser altimeter in order to see how deep the hole we have created is. So the departure will be, the final day will be 10th of May 2021, and then it's already decided sample return will be on the 24th of September 2023. This will occur in the Utah Test and Training Range close to Salt Lake City. And now what we are thinking is not just doing the sample, the sample acquisition on Earth, then it will be brought to the Johnson Space Center, where there are all the samples taken from the moon, but we will also start the spacecraft in order to avoid the Earth and trying to go in 2029 to asteroid Apophis to do a flyby or a rendezvous, and in order to maximize also the return from another different target, of course, without the sample acquisition. So with this one, I thank you,